So this is part of the Radius tutorial series, and maybe some of you have attended some of the tutorials already, and there's a few more coming up on Raja, Ascent, Axum, Weave, and Flux. Okay, but today we're covering Caliper, Hatchet, and Thicket. There we go. So I'm going to start with Caliper, which is our performance profiling library. I'll give maybe a half-hour presentation or so, and then we can jump into the AWS images and play around with Caliper live a little bit. And then Stephanie is going to take over for Hatchet and Thicket. Okay, so what is Caliper? Well, it's a performance profiling library. So the idea is that you can integrate performance profiling functionality into the HPC codes themselves. So that way, profiling is always available. You can essentially turn it on whenever you like, and that can greatly simplify profiling, especially for application end users who might not be familiar with complex developer-oriented tools. Caliper is also an instrumentation interface, so you have functions and macros where you can mark regions in the code, and you can use that for Caliper's own profiling functionality, or also forward this information to other performance analysis tools. So Caliper can kind of work as a common instrumentation interface. You don't have to instrument the code with several different APIs. And of course, it's specifically designed for HPC applications. So you have support for all the typical programming models like MPI, OpenMP, CUDA, HIP, and Cocos as well. And then we have functionality like call stack sampling, hardware counter profiling, memory profiling, and lots more. So what can you do with Caliper? So you can use it for basic lightweight always-on profiling, where you just print a performance summary report every time your application runs. You can use it for performance debugging, just digging deeper into what your application is doing. You can do performance introspection, so you can query performance at runtime and use it for tuning or things like that. We're not going to go into that in this tutorial, but it is something that Caliper offers. And one important use case for Caliper is actually comparison studies across runs. When we want to do scaling studies, regression testing, essentially comparing different programming inputs, then Caliper is a great platform for that. And that's because it's easy to automate, and also it can record not just performance information, but also metadata for individual program runs as well. So one of the goals we have is essentially enabling performance analysis as a routine activity in HPC software development. And we do this by automating a lot of steps. So we can integrate performance analysis into automated workflows like nightly testing. And we have done this with several Lawrence Livermore applications. So here you see an example with the nightly test performance of a LLML physics code over a period of 5 months. And you can see that there were some performance regressions at some point, and then things get better as the developers improve the code. So to that end, Caliper fits into a larger tool ecosystem that we have developed at Livermore, together with Spot, Thicket, and Hatchet. So Spot is actually kind of a web framework that we use for analyzing a large collection of runs, like for our nightly regression testing. Thicket kind of follows up on Spot in the same realm. So Spot works well if you are an LC user where we have an instance of Spot running, but trying to integrate it into your own separate HPC center is a little bit more difficult. Whereas Thicket is a Python framework that you can basically just install and run anywhere. And Stephanie and Olga, we're going to cover Thicket in the second part of this tutorial. Hatchet is kind of in the same realm, so that it is also a Python framework for analyzing call graphs. And that's very helpful if you want to dive into the performance of like a single data set, or maybe like 2 or 3. And Caliper in this realm is our instrumentation and profiling component. So this is actually the part that goes into the code and measures performance. Okay. So there are a few tutorial materials that you can follow along. So there's a GitHub link up in this slide here, and you also got it through the email. And You can, it's what we're using for the AWS instances later on, where you can play around with Caliper, but you should also be able to just install this on your own and follow the tutorial contents there if you want to just revisit those later on. So Caliper is on GitHub, that's its main repository and also the main bug tracker and so on. So if you have any questions, the GitHub discussion page on GitHub is the best place to go. If you want to report bugs, we're welcoming that a lot. And there also GitHub's the best place to go. But you can, of course, also just contact me directly. Okay. So any questions so far?
I had a small question.
Okay.
David, so in HPC settings, right, what kind of privileges would a user require? Like, I'm thinking in terms of if users would be able to use this to profile their own codes, because there are so many, right? So for us to go ahead and do it for them is one way to look at it. But does it require root privileges to draw metrics? What kind, if you could, at whatever point, touch upon it.
Okay, so also the default or the basic things like just timekeeping does not require any special privileges. So as a developer, you can link Caliper into the code and add, say, a command line flag that would enable performance measurements, and then users are just able to do them. So there are a few special cases where you run into things if you want to measure some system-wide hardware counters or things like that, or node-wide counters where sometimes privileges are restricted. There are a few ways around that, but that's those kind of esoteric cases would be the only ones where you need extended permissions, but not any of the default use cases.
So if somebody's testing their code, as long as they want to draw data regarding their code, it's fine. But if they want to dig deeper into the system dynamics, that's when in generic ways, you require root privileges. Right?
Yeah.
Okay, thank you.
Okay, so how do you usually use Caliper? So as I mentioned, it's an instrumentation library. So most of our instrumentation is actually manual. So you go into the code and pick regions that you are interested in, and then mark them with Caliper's region instrumentation macros. So they can live in the code and they don't really do much on their own. Caliper is entirely configurable at runtime. So at runtime, you can specify a configuration and telling Caliper how you want to measure things, and then it goes ahead and do that. So there are several ways to do that. You can use an environment variable like this config variable down there, and you can also do that through an API. So the code can actually itself tell Caliper to measure performance. So and in the end, we want to analyze what Caliper recorded. Depending on the configuration, Caliper can produce different kinds of outputs. And what did I just do here? Oh. Okay. I don't know what PowerPoint is doing, but we'll see. Anyhow, so depending on the configuration, Caliper can produce different kinds of outputs and produce just human-readable reports directly, or machine-readable files that you can process in tools like Hatchet and Thicket, and also in your own scripts. Okay, so as I mentioned, the core functionality of Caliper is actually its instrumentation API, so these region markers. In fact, Caliper started out as a performance profiling or an instrumentation library. And so we have a functionality where you can mark different regions in the code. So in the example here, we're creating a region called init around this do init function call. And you can use macros in C and C++ and functions in Fortran to do that. And there are also more different kinds of macros where you can annotate things like loops, loop iterations, and even things like really custom information, context information that you want to integrate into your performance analysis, like function parameters or something. So as I mentioned, by default, these instrumentation markers don't really do much. So typically it's fine to leave them in the code, although a lot of people actually make this a compile time decision and can leave out Caliper entirely. So how do you go about instrumenting a code? Here are a few guidelines. So first of all, it's usually good to be selective. So the usually you go instrument high-level program subdivisions like kernels, phases, and things like that are meaningful to you as a developer. The instrumentation is not really meant to pinpoint bottlenecks down to the source line level. If you need that level of detail, you can combine instrumentation with other things like sampling. And Caliper lets you do that. But yeah, generally, you want to get a high-level overview of the program performance or focus on a specific region with those instrumentation markers. That's actually kind of an advantage of manually instrumenting the code, so you can exactly define what you're interested in, and you don't get clutter from just having everything instrumented. And then, of course, you should use meaningful names that are useful to you as a developer. A lot of the codes that we are developing at Livermore are now advanced C++ that use Raja as an example here. That's kind of a template framework for iterations over various things. And using Caliper, we can give this construct a pretty meaningful name in our performance output and not some cryptic thing that a compiler generated for this. And of course, you can start small, so you can just start annotating a few regions and then add more instrumentation incrementally as you go. Okay, so once we have these instrumentation markers in place, we can actually measure performance. And there are a few different ways to do that. And the easiest way to go about it is to use one of Caliper's built-in measurement recipes. One example is this runtime report, and we can enable these measurement recipes with the Cali config environment variable. And in this case here, we're using the runtime report, which simply prints the time spent in all our annotated regions out on the screen in a basically human-readable hierarchical table, as you can see down there. So for an MPI program, it will automatically aggregate these times across MPI processes. And so there's a whole bunch of these profiling recipes in Caliper. So we have things like the runtime report that I just mentioned. You also have a loop report, an MPI report that can give you information about your loop iterations or MPI functions specifically. You can do sampling. So Caliper does support call path sampling as well if you need additional detail for all the code regions that you haven't annotated. You can do tracing and essentially create a timeline visualization. We'll look into that. And then there are several configurations that produce output for the Hatchet and Thicket tools and Spot. So there again, you can choose between just region profiling, where you're just focusing on your annotated source regions, or you can enable sampling with that as well. There's a Cali query program, so this can be used to actually analyze Caliper output, or also to figure out what kind of configuration flags that Caliper is built with, and give you information on how to use these configuration recipes. So most of the recipes can actually be augmented with additional parameters, and these parameters can then enable more metrics or change output features. So in the example here, we are enabling another metric, the memory high watermark, which gives us the maximum amount of memory that was allocated with malloc in every instrumented region. And we're also redirecting output to standard out. So there are a lot of these options available, and you can find out which ones there are with this Cali query command. So as I mentioned, you can do sample profiling. So here's an example output of these sample report configuration. So that can show you additional detail inside the regions that you have instrumented with Caliper's instrumentation markers. So you get the exact functions that were called, and you can also configure it to give you file and line numbers. So this is a good way if you need to find a specific performance bottleneck and you don't quite know where it is, just from the instrumentation alone. So you can do event tracing as well. So the event trace config basically writes every begin and enter event for each of the instrumented regions that you have. And then we have a converter script where you can convert these event traces into the Chrome browser's event trace format, and then you can look at it in the Chrome trace browser. or the Perfetto trace visualizer from Google. So this is not the most scalable thing, right? So this provides a JSON file, and that's just kind of limited in how large of an event trace you can generate. But for relatively small examples, if you just really want to see in detail what's going on in your program, that's a pretty useful option to have. Then I mentioned you can also forward Caliper annotations to other tools. So here we have an example with NVIDIA's NVProf tool. So there's a configuration for NVIDIA's NVTX instrumentation interface, and that would basically just go ahead and forward all of your Caliper regions to NVTX regions. And then you can see them in NVIDIA's tools like the NVIDIA Visual Profiler or the NVIDIA Insight tools. And the same thing also exists for AMD's stack. That would be the RockTX annotation API, and for VTune. So this is really useful because, well, you can now instrument your code just with a single instrumentation API and don't need to support all of them simultaneously. As I mentioned, there's quite a lot of built-in support for Hatchet in Caliper. So Hatchet is our Python library for analyzing call tree profiles. And we have a few configuration recipes that can generate output that Hatchet will digest. And you can then use all of Hatchet's analysis functionality to study the data that you collect there. You can actually also use Caliper to analyze a lot of these output features. So this is generally a good configuration to use, or a good set of configuration recipes to use if you just want to implement some automated analysis or write your own scripting in general to look at the data. Okay, so one kind of unique feature that Caliper has in terms of performance analysis tools is the config manager API. So that allows you to control and set up profiling within the program itself. So to do that, you can create one of these config manager objects, and you give it a configuration string that looks similar to the ones that we've used for the Cali config environment variable. And then you can start and stop profiling of these configurations whenever you want, and later flush output. So this allows us to essentially control profiling through different means. So you have a little bit more control as to where exactly you're doing performance measurements, and you can also use additional program inputs to enable profiling. So for example, we often use it to add a command line flag to an application. And we can now use that to pass in this Caliper configuration string and essentially control profiling through native ways for the application. If none of the built-in recipes do exactly what you want, you can actually configure Caliper manually. So most of Caliper's, or well, all of Caliper's actual measurement functionality is implemented in these little modules called services. And you can essentially compose and configure them individually in a lot of different ways. So in this example here, we're actually measuring memory traffic over unified memory between a CPU and a GPU. And we're mapping that both to the source code regions where they came from and also named memory pools. So you can see exactly where data was transferred between which two pools, and how much, of course, and how long it took. So essentially, you can configure Caliper like basically, a Lego toy. Basically, it can do whatever you want. Just have to reassemble it a little bit. But yeah, it's extremely flexible and can be used to build just really custom performance analysis solutions. Okay, so now a major focus of this tutorial, especially with regard to the other tools, is ensemble performance data collection. So where we're not just looking at performance of a single run of an application, but actually many of those, for example, for, as I mentioned earlier, scaling studies or looking at different program input parameters. So that is essentially what Thicket is designed for on the analysis side. So you can load a whole bunch of different profiles into Thicket and then browse through those. And yeah, I'm going to show you a little bit of the workflow and how we're actually collecting data for this kind of process. So we need 3 steps. So first of all, we're starting out again with region instrumentation. So we're annotating the code with Caliper instrumentation calls as usual. But in addition to those region instrumentations, we're also adding program metadata annotations. So these tell us more information about each individual run. And that then helps us compare and analyze all the data that we have across all the many different runs that we have for our application. So we're actually also putting essentially instrumentation calls for this metadata into the code. And we have a separate library call for that called ADIAC. And this, can record all kinds of different run information, like, say, the MPI job size, what machine is this running on, and also program-specific things like what is your program input deck. And then, as I mentioned, that's really helpful to compare things across all the different runs. And then, of course, we're going to enable performance measurements at runtime to collect the actual performance data together with this metadata that we put in the program. And here we're typically using the spot config, so that's left over from our spot days where we had mostly the web interface. But the same kind of data that Spot collects is also very useful for analyzing in Thicket. So you're doing this for a lot of different runs. You can throw all these files that Caliper produces into a single directory and then point Thicket into that and do your analysis of all the different data that you have collected. And of course, Stephanie is going to tell you more about Thicket later on. Okay, so just let me tell you a little bit more about this ADIAC library. So again, that's a library for C and C++. That's specifically designed to collect this kind of run information. There are two kinds of functions in ADIAC. There's built-in functionality to collect a common kind of metadata, like say the username, job launch date, MPI job size, and so on. And there's kind of this key value format that lets you record program-specific information for a specific run. So the kind of information that we typically collect includes kind of build information, like, for example, what compiler was used, what compiler version, what compiler flags. Then basically the execution configuration for the job. So that would be the machine it's running on, who's launching it, what's the command line that was used, and things like that, essentially. And then we have program-specific things, like that would be kind of the input deck that was used for the problem size, so anything like really specific to the application that would help you analyze performance later on. So Caliper includes this information in its output formats, and then we can also load it into Thicket. So here are kind of the different built-in functions for collecting common kinds of metadata in ADIAC. So we have things like the username, UID, launch date, executable name that was used, the command line, the cluster, the MPI job size. And we're also often collecting kind of global run performance metrics, like the overall wall clock time that was used, or a kind of an overall figure of merit for the code. And that's pretty useful later in Thicket to compare just the overall performance across many different runs. So then, as I mentioned, we have this key value interface for collecting program-specific things. The C++ interface takes a lot of different data types that it can put in there. So it can collect like integers, floats, strings, but also kind of complex data types. So you can put vectors in there. And ADIAC also has kind of, more specialized versions of standard data types. So you can tell it that this particular string is really a path name or a program version or things like that. That same thing exists in C, and here we're kind of using a printf style interface. So you can name your variable and then essentially tell it what data type it is. And again, we're supporting a lot of different both built-in and complex data types. Okay. So we're kind of halfway through, and then let's hope that we got our AWS setup done.
So David, there is a question that came up that you can answer. So someone would like to know about what if they don't have access to the application code? Is Caliper still useful in this case, or should they look to using a different tool?
So if we don't have access to it at all, then I'm afraid it's not going to work really. So I mean, yeah, so really the model is that you need at least some kind of instrumentation to at least get Caliper started. I mean, it can do a lot without putting much instrumentation into the code, so it can still automatically record MPI or CUDA information and things like that. But you do need something in the code right now to actually get it started. So if you really don't have access at all, then you tools like HPC Toolkit or gprof or that don't require source code.
Thank you.
Okay. Yeah, let me check if I got an invite to our radius deals. Here we go. All right. Let me stop sharing this PowerPointing and switch over to the terminal, hopefully. Let's see. And yeah, you can do the same. You should have gotten your login info. And then hopefully we can get going with that. So it's in. Okay. So let me share this thing now. I did my level still. Okay, so hopefully you're seeing my terminal. Oops. Oops. Let me just move this over to my other screen so I can face. Okay. So can you see my terminal now?
Yep, it looks good.
Awesome. So in this AWS environment, we have like a directory called op/Caliper tutorial. We can move in there, and you should find a script called setup-env, and you should source that. So not just execute, but source it with a dot or explicitly via source. And then you should have the tutorial environment loaded. So unfortunately, we don't have MPI support in this particular build of Caliper. We ran into the few technical snafus earlier on, and we tried to create this thing. But yeah, we can still do a lot of things without it. So the tutorial environment that we have here is the same that you find on GitHub. So you can actually, if you want to do this later on again, or look at the materials later on, go to that GitHub tutorial page, which is at github.com/DA/EHME, and then it's Caliper tutorial. So yeah, you find all the materials there, and you can then go through it on your own pace if you like. So what's in here? So this repository contains Caliper itself and also ADIAC and a few different example applications. So if you're looking into this applications folder, we have like a basic example, which is just like a little instrumented app. Let's just like take a look at that. Oops. So we see various little functions in here that all have these Caliper instrumentation markers. And we also have config manager support here. So when we give this program a command line argument, just the first one, it will interpret that as a Caliper configuration string. And yeah, then just run this particular configuration. And you also find some additional instrumentation macros here, like, for example, this loop instrumentation. Okay. So we can run this thing. So this is instrumented with Caliper, but if we run it without any options, then it will basically do nothing. So as I mentioned, by default, these instrumentation markers don't really do much. And you have to enable the configuration, which again, we can do with the static config environment variable. So if we give it a runtime report, then it will show us the time it spent in all these instrumented regions. And as I mentioned, we can also do this through the config manager API by doing a thread configuration string just on the command line. Should be doing the same thing. Okay. So as I mentioned, we can add various options to our runtime report. So for example, we can do a region count option. So this will give us the number of times a particular instrumented region was called. And we see, well, most of these were just one time, and this main loop outer thing, you should actually kind of ignore this kind of an artifact. But the functions were each called 4 times because they are running in a loop. So you can see all the options that exist with this query --help runtime report command, and we can type this here. So this will basically show all the options that the runtime report supports. Now, not all of these might be active, so a lot of these depend on additional build options, like for some you need copy support or MPI support or other different things, or well, for example. But there's a whole bunch of different additional metrics that you can add. You can record MPI functions. You can also be selective what MPI functions you want to record. You can report message sizes. You can look at OpenMP if you have OMPT support. That's the OpenMP user interface. And you can look at CUDA, HIP, and other profiling or, well, GPU interfaces. Okay. So that is, I think, what I had here. So let's look at another example app. So we also have English in here. That's in apps English. And let's just get in there. And here again, if we're can just run English using a few iterations only, because this is going to take a lot of time otherwise. And we can give it a runtime report. So for Ludash as well, we have added config manager support. So if you add this -P flag and give it a Caliper configuration, it will again and show us all the time in the regions that we have instrumented inside of Ludash. Let's actually just take a quick look at the code and look at ludash.cc. And in this case, you might know that we have after all this license stuff. So I have kind of an additional macro here. So here I've made the use of Caliper optional, so it's a compile time flag if you want to have Caliper support enabled or not. And if we do, then we have our Ludash specific instrumentation macro, and that just points to the Caliper annotation macro. And then we have annotated a few different functions in here. Right, this one, and you might note that when we didn't instrument all of the functions, just kind of the top level ones, maybe like half of them or so, and we specifically left out all the smaller functions that, this would create a lot of overhead or a lot of clutter if we would instrument them as well. Okay, so let's look at this main function here. Just really quickly, in this case, we have an additional, it's a little tricky. So we're adding a Caliper configuration that says that all our region instrumentations should be process-wide. This will help us if you want to look at threads that are launched inside these regions, because otherwise we would just get this information for a single thread, but not all of them. We're not going to get into that in this tutorial, unfortunately, but yeah, it's something to be aware of if you have a multi-threaded code that's annotated with Caliper. either make it so that all of the threads are annotated, or just kind of the main thread, and then use or OpenMP or sampling if you want information for the sub threads in there. And we're also recording metadata information here. I'll show you a little bit more about that later. And here we're basically initializing ADIAC as well as our Caliper config manager, where we give it the Caliper configuration string that was passed into the command line arguments. And yeah, then we have a few more things like we again have loop instrumentation here. And at the end, we're just finishing up Caliper. So as I mentioned, we also record the program run information for Lilash. That is actually done in this Lilash Caliper util.cc function. So there's this function called record globals. And we have several ADIAC annotations that, again, give us information or give us kind of common kinds of information like the MPI job size, what machine, and so on and so forth. And we're recording all the parameters that English can be configured with, like the number of threads that we want, the number of iterations that we want, the problem size, and so on. So all of these are command line arguments that are passed into English, and we're coding them in ADIAC, so we're later able to sort and compare our performance information between all those different things. If you want to, for example, see how much the problem size exactly affects your performance. We're also recording build metadata. Now this is a little bit more special. So the way we're doing this is we're actually using the CMake, the build system, to create us a configuration file, which is actually a C++ file. So there we're putting in various variables that are filled out by CMake. So it will put in the compiler name, the compiler version, who built this program, and what are the compiler flags, and so on. So using CMake is just one way to integrate this compiler information into the code and into ADIAC, and then later into the performance data. And you can do that all automatically, nicely enough. So that's a pretty convenient way to go. So let's give English a try again. So we did our 10 iterations here. I think it's a runtime report, and actually use the metadata, I think, option. And that will actually show us what kind of metadata we reported. And yeah. So yeah, we see that as well. Using Caliper 2.10, we have a few global performance metrics that we recorded with ADIAC. That's like the global figure of merit and the overall elapsed time of the code. And then we have like the compiler information, all of our input flags, and the command line, and so on. In addition to, of course, the profiling data that we collected. So there are a few other, well, not here. You can try the memory watermark that should actually be broken here. Oops, clicking slide. That's not. Okay. So yeah, this is a really very basic configuration of Caliper that basically doesn't support anything, unfortunately, except for basic timing and so on. All right, so Sakni, you have a question?
Hi, David. Yeah, one quick question. You are going through all these applications, but these data are they being generated by Caliper somehow, or these are just the basic application and you're showing us what the application does?
So let's take a look at that again. So the first part of the output here is generated by Lilash. So basically everything up to here. And this part comes from Caliper. So this is what the runtime report would print.
Okay, so you do not, so like, for instance, I've played around a little bit with the profilers of the other companies like UProf by AMD. So you usually have to call it, like the first call has to be to the profiler and right. Some arguments, and then finally your application binary. So in this case, I see you directly went to Lilash 2.0, and there is no call, like visibly, I'm not able to see a call to Caliper. So how did that work?
So that's our config manager configuration API. So in the program, we're going ahead and configure Caliper to do this thing. So we can take a look at that again. So we're creating this config manager object in the code. So we do actually have to write that in the code. We're parsing in the command line argument. So you might have noticed this dash capital P flag where we put in the runtime report as a command line argument. So we're giving this to the Caliper config manager. Then we're starting profiling. And then at the end, we are telling Caliper to write this recorded performance data. So we're kind of doing it through the program, through the API, but it was Caliper that collected all this data and produced this report. Does that explain the question?
Yes, thank you.
So again, you don't need to do that. So you don't have to put the config manager in the code. So you can also use the Cali config environment variable. And this. And it's going to do the same thing essentially. So it essentially works because Caliper is a library and not a third-party tool that is really only enabled at runtime. But because Caliper is compiled into the code, you don't need technically, if you're using the config manager, any kind of prefix or something like that. It is the way that HPC Thicket or Tower or something would work.
Okay, thank you so much.
Okay. And I think. Yeah, so I mentioned there are a few different other configurations that we can use. For example, instead of the runtime report, we can use the spot config and looks like I don't have write access to this directory. That's a bit unfortunate, but what we can do is type the spot config output, use that out. So then, if we're using the spot config, Caliper would kind of write a machine readable file that we can then read into Spot, and we can actually also look at this file with the Cali query program. And if we give it the -3 option, then it'll print essentially the same data that the runtime report created. So by default, the spot config basically does the same thing that the runtime report does. It collects the time spent in each annotated region. In an API program, it goes ahead and aggregates that across ranks, and then just writes it in the file. And like the runtime report, you can also give it a lot of options to enable additional metrics and so on. That's basically the way to produce data for Spot and, as I mentioned, for Thicket and Hatchet. You can use the Spot config, the Hatchet region profile, or other things to look at the data in any of those scripted tools or write your own scripts for it. Okay. Let's briefly look at another little example application. So we're not actually going to be able to run this one either, unfortunately, because we don't have a CUDA instance. But here we have the access bench program. That is a CUDA application, or well, it can be a CUDA application, and here we're using it in the CUDA configuration. And here I can show you a little bit on how you would analyze a GPU code. So again, we put some region instrumentation into this code. So all of the actual kernels of access bench are implemented in the simulation.cu function. And let's go further down. Okay, so and the code has various different implementations for its core algorithm. And I've instrumented each of those with Caliper annotations, and you see that we have like a global region annotation, or well, a top-level region annotation around the variant of the kernel that was used for this particular function. And then inside there are more Caliper annotations around each actual CUDA kernel that is being invoked. So I do actually have some output for this code, which should be in here. Yeah. So we can typically run a runtime report for this code. Looks like this. So again, we're actually also recording metadata with this program. Again, the same kind of thing, like what machine is this running on and the program input parameters. And this is kind of the main annotated regions that we have. So we have a main function, we have a simulation. And in this case, we use this algorithm number 4. And inside there, you see the additional Caliper instrumentation for all the different kernels that we for all the different CUDA kernels that the program launches. And most of the time is actually spent in this lookup kernel thing here. Okay. What if you want to see more? So there's an option for the runtime report that's called the profile CUDA. So kind of. Essentially like this. And if you do that, then it will show us the time that we spent in the CUDA host side API call. So we now see all the functions like CUDA device synchronize, CUDA malloc, CUDA free, and so on and so forth. And we see how much time exactly we spent in those. And we see for our lookup kernel, of course, we're spending very little time in the actual kernel launch, because that's, of course, an asynchronous kernel. And most of the time it is device synchronized later on. So we can actually look at the time that was spent on the device as well. So Caliper has support for the CAP-D profiling interface, which is NVIDIA's, profiling toolkit that gives you a lot of data about the GPU activities. And there's a configuration called the CUDA activity report. And that essentially shows us what is going on in there. So let's take a look at that. So now you'll notice that we have a few different columns up here. So we have the host time. So this is the time that we spend on the CPU, essentially. Then we have this GPU time column, and that tells us the total time that we spend on the device. And both of these metrics are inclusive. That means we aggregate them across the entire program. So we see that for the total program, it took like 65 or 0.65 seconds in main, and 0.13 seconds of those were on the GPU. However, for our simulation and our algorithm itself, it was pretty much equal. So there, about 90% of the CPU runtime were really spent on the GPU. So we can, again, look into all the individual CUDA kernels that we have annotated. So let's take a look at the lookup kernel again. And here we now see that, well, it in total spends 0.1 seconds on the host, and also pretty much the same amount of time, 99% pretty much on the GPU. And we can see if you look at these individual functions, well, we spent very little time on the host for the launch kernel call, obviously, but the GPU time essentially shows you the amount of time that was, the amount of GPU activity time that was launched from here, and that's our 0.1 second. So we're launching 0.1 seconds worth of GPU activities in this particular kernel from this launch kernel call, and then we're just going to sit and wait until the device synchronize on the host. And you might want to know why we are overall spending so little time on the GPU for the whole program implementation. Well, a lot of that additional time is spent in the move simulation data to device function. Where we're actually sending 250 megabytes, I believe, from the, another column for that, from the CPU to the GPU, which kind of makes sense. that takes a little bit of time. And then some more time is spent in this function that we're not supposed to profile. Okay. You can actually look at the individual CUDA kernels themselves as well. So there's an option for the CUDA activity report that's called show kernels, I believe. And that shows us a little bit more detail still. So now we see the individual CUDA kernels as in the functions. Well, how they call it? But the main CUDA kernel entry points, essentially function names that we called in our code. And yeah, again, this kind of display is inclusive. So under main, we see the total time spent in each of the different kernels anywhere in the program. And as we then go down into the tree, we see specifically what kernel was launched from which of these individual annotated regions. So the lookup kernel region, we just launched logically this access lookup kernel function. Okay. So that's basically all I wanted to show. Do we have any more questions? And again, feel free to play around with this on your own if you like. So if you have a system with CUDA or MPI, you can enable the CUDA or MPI version for the tutorial materials, and then you can actually play around with these options live. So I apologize that this wasn't really possible in this particular setup here. But I hope you got an impression on how technically it works. And again, you can look at commands like query configs. That shows you all of the different profiling recipes that are there. So we have this event trace, for example, or the Hatchet region profile, and all of the different options that there are in principle. Oh, one thing I can show is actually the loop report. So let's quickly do that. So if you remember, we have these loop instrumentation annotations in Ludash, for example. And we can configure it to give us information about, say, every 10th iteration. And yeah, you now see from this loop report, the total time is spent in our main loop, essentially. So that's like 3.23 seconds. And we see, how much time. And essentially now tell performance over time in your main loop, like if you have a program that starts out fast and becomes slower and slower and slower, you would be able to see that with the loop report, or vice versa. It's just speeding up. You would also see that. Now, Luda is pretty constant, so you see that essentially you're spending the same amount of time in each of our iteration blocks here. Any additional questions? If not, I think I can turn it over to Stephanie and Olga, who are going to continue with the second part of this tutorial covering Hatchet and Thicket.
All right. So to continue our tutorial, I'm going to be talking about some additional performance tools that are meant for programmatic analysis of our hierarchical data, such as what's being collected by Caliper. So in this part of the tutorial, I'm going to be talking about our tool called Thicket, and I'll also be covering a little bit about Hatchet as well. So again, for those that might have missed this in the beginning of our tutorial, we'll be running, or the Radius group at Livermore will be continuing to run some tutorials the rest of the month. So if you haven't had a chance to register, please use this link here to register for some of the upcoming tutorials. So I'm going to follow a similar format to David. I'll give a presentation for about 30 minutes talking about an overview of Thicket and our constructs. And then I'll have us hop over to actually a binder environment instead of an AWS instance for us to play around in a container environment that will have our Jupyter notebooks, a Thicket installation, and all of our dependencies. The other thing I do want to mention, we are planning to set up a mailing list for us to announce release notes and updates related to our performance tools for Caliper and Thicket. So if you are interested in being on that mailing list, here's a shortened bit.ly link that you can add your email, and then we will set up the mailing list following this tutorial. Okay, so let's get started. So the challenge that we are trying to solve with Thicket, or that we see with Thicket, is that our trying to do performance analysis is becoming more complicated, especially in our growing software ecosystem. So within HPC, we have an increasingly more complex software and hardware stack. And so the amount of things that we're trying to understand continues to grow, right? So we want to do strong scaling and weak scaling analysis of our applications. We'd like to also understand how, if we change application parameters, how that impacts our performance. We're interested in varying our compilers and our versions of those compilers, as well as the optimization levels. We're interested in the performance of our codes running on different hardware architectures, such as CPUs, going to GPUs, or even just changing across different CPUs. And then we also have available to us different tools that we can use to measure the application performance within different aspects. And so, right, David had mentioned a couple, right? We talked about Caliper. NVIDIA has a tool called NVIDIA Insight that maybe we want to measure our application with to get GPU performance measurements. And if we instrument our codes or measure our codes with these different tools, then we get profiles that have been generated from each of our studies. And so our overall goal is to be able to analyze and visualize the performance from all of these different inputs, different sources that might have different data as well. So our big picture solution for analyzing and visualizing this performance data is shown here. So steps 1 and 2 is us instrumenting our code or collecting performance profiles using different tools, whether that's you having to instrument your application or having an external performance tool that can collect this information. And we assume that within each of these profiles is one particular run of your application. So if you're running a strong scaling study or a weak scaling study or wanting to vary across different compiler optimizations, you would have a separate profile that's been generated for each of those. And then once you have this collection of performance profiles, then you can load that data into our tool called Thicket. So this is a post-processing analysis tool that's built in Python. And so Thicket includes 3 different tables. So we have a table that stores all of your performance metrics, such as how much time each function took or how many cache misses you have. There's a table to store the metadata about the run. So David had talked a little bit about that with the audioc library. So this is information about where the profile was generated, who ran it, how many ranks were used, what the command line options were, so on and so forth. And then Thicket also has a third table that's this aggregated statistics, and that's an order reduction over your performance data table. So if your performance data included data from 10 different runs and you wanted to know what the average was, that number would be stored in your aggregate statistics table. And then once you have your data loaded into Thicket, we're providing a bunch of exploratory data analysis capabilities so that you can explore your data, make figures and plots, be able to manipulate your object and filter down to the particular nodes or metrics of interest, as well as be able to apply clustering mechanisms and performance models. So what do our profiling tools collect for a single run? So in the case of Caliper, within Caliper, you're getting a call tree shown on the left. And so this is telling you which functions are calling other functions. So main calls foo, main calls bar, and then bar also calls baz would be what's stored in our call tree. And then for each node in that call tree, we have a list of performance metrics. So like I said, this could be the time that it took to run the particular function, maybe how many cache misses or memory accesses that you had. And the third thing that our profiling tools are collecting is this metadata about the run. So this is the global information about how you run it, so that you're not having to, embed all of this information in the profile name or having to keep a separate README about how you ran the particular profile. If you embed all of this into Audiac, for example, into your code, then you can start to report information about how you built this application, who ran it, how did you run it, how many ranks or how many threads did you use, and maybe even what is the date that you ran the particular run if you're interested in this performance study over time. So all that information gets embedded into the metadata. Thicket, the tool that we're talking about now, actually builds upon Hatchet, which is also part of this tutorial. So in Hatchet, the object over there is known as a graph frame. And the graph frame consists of two components. So you have this graph structure, which is storing the relationships between the parent and the children. So again, main is calling physics, main calls solvers, solvers calls hyper and MPI. And then the other object or the other component within the Hatchet graph frame is this performance data table that's storing any of the numerical or contextual information that's associated with each function or each node in the call tree. And so you might also have information per rank or per thread if you're running your application in that way. And so if you're interested in links to information about Hatchet, those are there on the bottom. So we have the Hatchet source, which is the first link. And then we also have a binder environment for Hatchet as well. Hatchet was our programmatic analysis tool that we initially built in Python for us to do comparisons across one or within one or across between two performance profiles. But as we started to talk about the scale of performance profiles that we're collecting, we really needed another tool to fill that gap, and that's where Thicket comes into play. But if you're interested in looking at using Python to analyze your performance profile, Hatchet can be really good for that as well. So if you want to visualize Hatchet's graph frame components, we have two mechanisms. So if you're reading your data into this graph frame called GF, then if you want to print the call tree, you call this .tree function, and that'll render you a terminal-based tree as shown here on the left. The coloring, of course, is related to this legend. This is just the default color map and scheme, but there's other parameters that you can pass to the tree function to change this output if you want to customize it a bit. And then the performance data table, again, is a pandas data frame. And so you can use the native Python data frame print to be able to print out the table of metrics that's associated with it. So for every row in this performance data table, that'll align to a element or a node in this tree. So like I mentioned, Hatchet was really useful for us to be able to programmatically analyze between two profiles. So this is one of the canonical examples that we show when we're talking about this. So within Hatchet and also within Thicket, we're comparing these profiles on the basis of the call trees. So you can think about this when you're wanting to do, let's say we want to divide two of our profiles and we want to compare, what is the speed up of going from my CPU performance profile to a GPU performance profile. The first thing that we're going to do in Hatchet, let me go ahead and move this down a little bit. So if our tree structures look like this on the upper right, so we want to divide a graph frame that has 3 nodes, foo, calls bar, calls corge, and we want to divide that by a graph frame that has 4 nodes, foo, calls bar, calls baz, and grout. The first step of our division function is to first unify across these two graphs. And so that's our resulting graph here on the just underneath in the upper right. And once we have unified our two trees, then we can perform the division directly. So yes, it's animated. So if we have a node that exists in both of our graph frames, GF1 and GF2, then we're going to do a straight division of the metrics. So 6/3. And actually our result is here on the left. So our bar node as a result will have a value of 2. And then if we try to divide nodes that only existed in one of our two graph frames, so in this case, we have an extra Garpley and Grout node that only exist in graph frame 2. What Hatchet's going to do is assume that there's a nan for the nodes that are missing. So the result of a nan divided by anything, or the result of any arithmetic operation with a nan will be nan. And then what Hatchet will do is annotate the resulting nodes to indicate which tree it came from. So in this case, because Garpley and Grout came from GF2, this is what we're calling the rightmost operator. And so that's why we have a green arrow that points to the right. So this is an example for division, but Hatchet also supports other arithmetic operations in the same way, and it will perform the same unify first before it does the actual operation. Okay, so now let me talk about how we compose multiple performance profiles in Python. So previous slides were looking at what a single profile collects and how we might compare two profiles at a time. The challenge is, the challenge with Hatchet was that the graph frames were separate pieces. And so besides doing comparisons, of division or addition, subtraction, you really didn't have all of the data in one location. And so that's where Thicket starts to fill that gap. So in this example, we're going to walk through how Thicket can compose multiple performance profiles in Python. So in this example, we have two profiles, P1 and P2. And for each of the profiles, we have a set of metadata, a tree, and we have a set of performance metrics. And so what Thicket is going to do first is compose our set of performance metrics into a single table. And the index, of course, will be that we have all the data for profile 1 and all the data for profile 2 for each of the nodes that we have in our call tree. And because these call trees are the same, we just have the same number of nodes that we have in each of the profiles. So profile 1's 24 cache misses becomes a row in the bigger performance metrics table, and 16 from profile 2 also becomes an element in this table. The next thing that Thicket will do is compose the metadata. And so this is just by taking, basically combining joining the list of metadata from profile 1 and also append the metadata that's associated with profile 2. And then the last element of our Thicket object is the aggregated statistics. And again, this is an order reduction over the performance metrics table. So in this case, with our performance metrics, for each node, we have two profile data. So we have a number of cache misses for profile 1 and number of cache misses for profile 2. And in our aggregated statistics table, since we're looking for the average, we'll take the average over the cache misses and append that singular value to the node main. So the Thicket components are interconnected. And so what we mean by this is if you affect or filter or remove rows from the metadata or the performance metrics, the associated elements within that Thicket object will also be updated. So as an example, what you can do in Thicket is, let's say that you have metadata from several different runs that you've loaded into Thicket because it's all in the same directory. And for your particular analysis, you're only interested in the metadata or the profiles that are associated with a particular platform and that were run by a particular user. So we can filter the metadata table to look for a particular platform. So in this case, we're looking for Lassen, and we only want the profile that was run by Bob. And so by applying that filter, you can see that our metadata here on the right now only contains one profile. And then our filtered performance metrics will also only contain the metrics associated with that profile as well. So this can be really helpful if you are tossing all of your Caliper, or I guess all of your performance profiles into the same directory. You can basically have your script load in all of your profiles, and then your programmatic Python code does the filtering for you to, pick and choose which performance profiles you want to look at for that particular analysis. So you don't have to keep record in your directory structures or in notes, on your machine of which sets of profiles were generated when, or, within a particular platform or a particular user, for example. If you have all the metadata that's generated in the profile itself, then you can filter and organize your profiles within Python and using Thicket. So we're really trying to hit hard on encouraging our applications to have metadata information because it can be so useful in helping understand and manipulating your objects in Thicket and doing your analysis. All right, so Thicket, now we've talked about the Thicket objects. So Thicket really enables exploratory data analysis of our multi-run data. So we talked about the Thicket, I'm trying to move WebEx, hang on. Okay, that's not doing what I want it to do. Okay, so we talked about the data getting loaded into the Thicket object, which has these three different tables: the performance data, your metadata, and your aggregate statistics. And this lets us compose different data from different sources and different types, looking across different number of ranks, varying the parameters within our application, varying compiler versions and optimization levels, and also being able to compare performance metrics across different architectures as well. And once you have your data loaded into Thicket, then what becomes available to you is this growing list of different data analyses. So we'll run through in the next few slides some of the initial analyses that we're providing for us to be able to manipulate and visualize the data and perform some performance modeling and clustering examples within Python. Before I jump into that, are there any questions?
Don't see any yet.
Okay, and let me see if I can fix my screen while we're doing this. Okay. Okay. All right, then I will continue forward. So we have been looking at two different case studies for using Thicket. So the first case study uses the Raja Performance Suite that's also developed at Livermore. This is an open source suite of loop-based computational kernels that we commonly find in our HPC applications. And this is helping us to showcase the performance of different programming models like OpenMP and CUDA across different hardware. So in our set of runs, we had a total of 560 profiles that we generated, varying the clusters that we ran on. We ran on Quartz and Lassen, as you can see down here in the table. Below, we had 4 different problem sizes for Raja Performance Suite. 3 different compilers were used, 4 different optimizations, varying the number of OpenMP threads, as well as the number of, or the block sizes for the GPU runs. And then the Raja Performance Suite has identified different variants, so we're varying across those. And this gives us the number of profiles that fit within that combination of metadata. And so we're going to use Thicket to analyze within sets of these runs. So how does Thicket compose multi-platform or multi-tool data? So in this example, we have two different Thicket objects that we've constructed. So the object that's sitting up here is the performance table, and we have two profiles that were run on our CPU. And we've greatly shrunk how many nodes we're showing in this case just for space. But for our accumulation node, we ran a problem size of 1 million and 4 million. And then you can see that the columns that are following are all related to the CPU that we're running on. So we get exclusive time. The number of reps is a Raja Performance Suite parameter, but we also get retiring and backend bound, which are two of the metrics from our Intel top-down analysis that we'll look at a little bit later. Our other Thicket object contains two profiles, also run at 1 million and 4 million, but these were run on the GPU. And you can see now that the metrics have changed to be related to GPU performance. So we get time on the GPU for each of these nodes and problem sizes. And then we get 3 different GPU-related metrics, such as the memory throughput and the DRAM throughput. And so now what we'll do in Thicket is be able to compose our CPU and our GPU profiles into a single table for us to do analysis in a more streamlined way. And so the CPU data, which was the table up top, we bring down into our final table. And then again, because we're composing our Thicket objects on the basis of the nodes or the call paths, we can simply take our GPU data and extend our CPU Thicket object with the GPU-oriented data in this way. So the first set in our row, again, is the CPU data that came from our Thicket object up here on the top. And then because our GPU has the same nodes and the same problem size, it has the same index, we can extend the CPU line with our GPU metrics here. And now we have all of our information in a single table, and it becomes much easier for us to be able to compare and be able to make plots and do column analysis here. Let's see. So within the Raja Performance Suite, we're going to now look at a slightly more complicated example of this. We're now trying to compose profiles from 4 different types or 4 different runs and be able to compose those side by side for us to do a CPU to GPU performance analysis. So our 4 profiles that we're composing here will be a basic CPU run using Caliper. We have another run also run on the CPU, but we're enabling the PAPI module in Caliper to be able to collect top-down metrics. And we do these separately because there is a little bit of an overhead with collecting with the PAPI counters or turning on the top-down module in Caliper. And so we didn't want the time for the top-down analysis to be the raw time of the CPU performance. Our third type of profile is a GPU performance, also from Caliper. And then our last profile is the GPU metrics, which are separate from what's collected by Caliper. These are collected from NVIDIA's Insight Compute tool. And so again, our analyses that we're doing here is to compute the CPU to the GPU speedup. And we also can correlate the memory and compute usage between these 2 architectures. So our table that results here, we're now just looking at a single problem size of 8 million. We have 2 nodes here, and you can see that there's 4 different profiles that we've constructed in our table. So we've got our CPU only run metrics here. You get exclusive time, and then these bytes per rep and flops per rep are part of the application itself. We get the CPU top-down metrics, retiring and backend bound. Our third set of metrics is the GPU runtime that's collected from Caliper. And then our fourth set of metrics are coming from Insight Compute here to provide additional analysis about the GPU performance. And then what we can do is, because all of this is in the same table, we've collected this derived column here. We've collected this or created this derived column here called speed up, and we can do our CPU over GPU time to be able to calculate that. And then what we can do is, because we have additional information about different counters from the CPU and the GPU, is we can start to better understand why the speed up of a particular node is the way that it is, right? So in our case, our Vol3D node had a better speed up than the Hydro 1D, and we can look to perhaps this DRAM throughput metric to understand why that's the case. So one of the other things that you can do in Thicket is filter your call path using our call path query. So if on the left side, this is our input call tree from the Raja Performance Suite, maybe this is too many nodes for us that we don't want to be looking at all of them. We can call into our call path query and basically be able to filter this on the basis of nodes. So in this example, we are looking for a node that's named base CUDA. So we're going to grab the root node and put that over here on the right side, which is our output call tree. And then the next thing that we're looking for is a node that has this block 128 at the end of it, and grab any of the nodes in between. And so what that's going to do for us is basically grab us one child from each of these subtrees, as well as the parent, so that we can get just block 128 nodes in our resulting call tree. And so this can be really useful for, again, filtering the number of nodes that you're looking for. If you're interested in particular subgraph within your larger tree that you know about, it's really helpful to be able to use the call path query. And there's a lot more information about the way to write these queries in our dialects, and that paper is here on the bottom right. And I have these slides up so you can reference them following the tutorial. So we also did, with the Raja Performance Suite, some analysis on Intel CPU's top-down counters. So if you're not familiar, the top-down analysis that's shown here in the upper left has essentially divided or identified the counters in a hierarchical fashion in order to identify bottlenecks within the code. So basically everything retiring, bad speculation, front-end bound, and back-end bound, and below are all different counters that you can collect on the Intel CPU. You've been seeing a lot of us collecting retiring and back-end bound in some of the earlier slides. So if we're looking initially at our top 4 counters, if one of them is coming up with a high percentage, we might want to collect additional counters, or at least look at the additional counters that are underneath, let's say back-end bound, in order to determine where we might be stalling. And so you can use Caliper's top-down module, which will use PAPI counters to collect the top-down metrics for these different call tree regions. And then within Thicket, we have this tree plus table visualization that's shown up here on the right, which is showing our top-down metrics as these stacked bar charts. So you have the problem size of the Raja Performance Suite on this, larger x-axis. So this is 1 million, 2 million, 4 million, and 8 million. And then on the y-axis is your percentage here. And so each color within our stacked bar chart relates to our 4 top-down counters. So retiring, bad speculation, front-end bound, and back-end bound. And each of these bars is a different profile that we've collected from Caliper. And so you can easily see, 40 profiles per node, and be able to look across the different colors and identify differences in their execution behaviors. So if I look at apps vol 3D, I see that it's more or less evenly split between being retiring, which is blue, and back-end bound as you scale the problem size. But then if I look at Hydra 1D, let's say, I can see that it's much more backend bound and perhaps more memory bound. And becomes more memory bound as you scale the problem size. So we can easily see just some differences in the different kernels as we look at this tree plus table visualization. So because Thicket is built in Python, we can leverage different third-party Python libraries to provide additional exploratory data analysis. So in this example, we're bringing in scikit-learn to do k-means clustering on our Raja Performance Suite data. And so this example, we filtered our data using the metadata to filter to those profiles that had an 8 million problem size. And then we use the call path query language to only look at our stream related kernels. So those are down here on the right instead of the big tree. And then to our data in Thicket, we applied scikit-learn's clustering to the top-down metrics to compare the performance of our runs or of our kernels at different compiler optimization levels. And so if we look at these two, we're only looking at two of the top-down metrics here because the other two weren't quite as interesting. But if we look at these, we could see that we have 3 different clusters that our k-means algorithm identified. So cluster 0 is our circles and includes our add, copy, and triad nodes. We had another cluster that includes our -O0. And then we had another cluster that includes our dot and our multiply nodes as well. And so we were finding that overall our -O2 optimization levels was performing the best for the 5 kernels that we were looking at, which is just something interesting for us to take a look at and dig in on. So our next case study that we used for Thicket was with Marble. This is a multi-physics code that's also being developed at Lawrence Livermore. And in this case, we have a total of 60 profiles that we wanted to look at, again, spanning multiple clusters, 2 different MPI libraries, and doing different scalings, as well as multiple trials for the particular configuration to compare or to look at noise. So our first thing is we wanted to compute the noise as well as look at scaling. And so we can use our group by function on the number of ranks to generate a table. I guess each table will contain only information related to that particular number of ranks. And then we can compute the noise by taking the average on our total time column. And then we can construct the runs across the different platforms, being CTS as well as AWS, and at different scales into a single table, and then use matplotlib to generate a strong scaling plot like what you're seeing here on the right. And so our deviation or our noise is shown in the shaded region here. And then each of the dots that you're seeing on the line is our average across the 5 runs. So what we were doing up here on the right. Another third-party library that we're taking advantage of is an open source library known as XtraP. And XtraP is for deriving analytical performance models from a set of profiles that you can vary 1 or more of the parameters. And so again, this is on the Marble data. And so for this one, we were comparing performance of AWS to a run on CTS. I think they ran on Quartz or one of our Livermore systems here. And so we're looking at a particular function, which is this multiplication or this mult function down here. And we call XtraP to look at the performance model based on this average time per rank metric. So each of these dots here is the average of 5, and then the XtraP line here is what's been plotted in blue. And so we can easily be able to generate or collect metrics on smaller number of ranks and then leverage extra P to be able to extrapolate to the performance at higher rank counts. So another visualization that we have in Thicket is this parallel coordinate plots that's shown down here on the bottom. So this is a snapshot from the parallel coordinate plot being shown in a Jupyter notebook. So it's an interactive figure and can be really helpful for showing the relationship between different metadata variables that you've recorded about the run, as well as being able to understand how changing different metadata metrics can affect your performance. So you've got in the parallel coordinate plot, or I guess in this visualization, you have two scatter plots on the upper, around the top of this. So you can change X and Y axis for both of these. But in this case, we're looking at the number of the max number of elements, which is coming from our application as it pertains to the exclusive or the inclusive execution time. And then we're also looking here on the right about the average inclusive time as it relates to, this should be number of ranks here on the x-axis. So this is I need to fix this typo. And so what you can do is drag across all of these dots to be able to select them. And that's where the colors will appear. When you initially do this, it'll be in grayscale. And the colors are helpful because you can then start to see how these different metrics and between the metadata and the performance data interact with one another. So in this example, we've selected to color by the architecture. So if you look at the parallel coordinate plot down here, I think sometimes you see parallel coordinate plots and the bars go vertically. Due to space constraints, we've decided to do our parallel coordinate plot horizontally. So each of these lines here is a different metadata value. So the first line is our architecture, second line is MPI world size, and so on. And then you can see that like on the architecture parallel coordinate plot, it has two values. You've got the RZ topaz here on the left, and you've got the AWS system on the right. On the MPI world size, we do have a tick mark for every unique value spanning between 0 to 2400. And so once you color by these lines, or color, let's say, by the architecture, we can easily start to follow or trace a colored line across these different metadata values to understand how they interrelate. So by doing this tracing, if I looked at RZ topaz, what I'm seeing is that the wall time of my RZ topaz tends to be larger than AWS just by doing this, tracing the orange line down to my different wall times. And so this is just another way for us to be able to look at the available data that we have in our set of runs. So to summarize, Thicket is a open source toolkit for exploratory data analysis of our multidimensional runs that we've built in Python. We've shown how to, I guess David showed you how to collect metrics and performance profiles using Caliper. And then within Thicket, once you have all those profiles, we're able to load those in and then be able to take advantage of some of the analysis tools that we've developed in Thicket. And this is consistently growing as we start to get new requests and requests from the community. So it's always changing. So before we dive into hands-on, I think I have one last slide. For our LC users, we do have this workflow that David had shown earlier about this automated application performance analysis workflow. So if you are an LC user, you can go to this, you can access Jupyter notebooks using this link, but you would have the Caliper instrumentation that's instrumenting your application and collecting profiles. And then once you have all of your profiles, we can load this up into Jupyter, and we have some Thicket templates for you to sub out your data and be able to have some initial Thicket analysis workflows. Okay, so for the hands-on, if folks can go to this GitHub link, so it's github.com/llnl/thicket-tutorial. In the README, there will be a badge called Launch Binder that you'll click on. And then this is an extra plug to please join our mailing list. If you're interested in release notes from Caliper and Thicket, we'll be sending those out through this mailing list and creating the mailing list following the tutorial. So let me switch. And I can take questions if folks have those. So this is the GitHub link. And so you can click this Launch Binder badge, and that will spin us up a binder repository with all of our, okay, well, limitations. Okay, I'm not gonna be able to run through them this way, but hopefully folks have been able to. So let me do it this way. Okay, so this is our Thicket repository, or sorry, our Thicket documentation. And on the left side under tutorials, I've added a page for tutorial materials that I will need to update, but the slides that we're presenting today are here for Thicket for you to be able to pull down and look at your leisure. You can ignore the Docker run commands. We had some technical issues this morning, so we're not going to use that this time. We'll just use Binder, so hopefully some folks have been able to pull that up at their end. And on our Read the Docs page, we actually have also under tutorials, these are the same notebooks that Binder is using, but on our Thicket Read the Docs, this is showing them how once they're actually run in the environment. So if you're not able to launch Binder at this time, you can walk through this tutorial with me over in Read the Docs. And we'll walk through the first 3 tutorials today based on time. We'll see how we do. But we'll start with the basic Thicket tutorial, which is our Thicket 101. And so I'm going to be showing this in Read the Docs, not in the Jupyter environment, but it will look similar to how it looks in Jupyter. So at the top of our notebook, we'll be importing any of our packages. So the key things that you will need would be importing Hatchet as well as importing Thicket. And then our next step, we're going to read in a set of performance profiles. And so for this case, we're creating 2 Thicket objects. One is generated, and so this is for the Raja Performance Suite. So we have a set of profiles that were generated with 1 million problem size. So we have multiple trials of that in one Thicket object. And then in our next Thicket object, we are, sorry, those are the files. In our next Thicket object, we will have a combination of files from 1 million and files from 4 million. The help command that's shown here in cell 3 can be really helpful. This is native to Python, but if you're, forgetting or want more information about the parameters or return types of a particular function in Thicket, you can call help on, let's say this TT is our Thicket, TT is our Thicket import package name. So you can do TT, and median is a Thicket function. And so we can call help on it to be able to get a doc string to understand, here's our parameters, here's the description of it, and what the arguments are. And then we will walk through here in section 4 the different components of within Thicket, right? So Thicket has 3 different tables. The first table is the performance data to store the multidimensional performance data from our profiles. The rows in each of the rows in this table represent a node in our call tree. And so in this example, we have multiple nodes here in this node column. And for each of the nodes, we have 3 different profiles. So that is 3 different, in our case, Cali files that we've collected. And so that becomes an additional index into this table. And because this is a pandas data frame, you can simply you could add a print at the beginning of this, or just run a cell that's just calling the data frame itself in order to get this to render. And I guess the other thing to note in Thicket, as you can see, is in Thicket, we're storing the profile as a unique integer or a unique SHA, essentially. You do lose, like we were talking about, the importance of having the metadata embedded into your application for us to be able to filter on. Basically, the idea is once you read in all your profiles into Thicket, you don't need to reference the file names of your profiles in order to get at, be able to remember, oh, this data came from this particular Caliper file. You can basically use the metadata information to be able to determine which file you need to be looking at. Okay. So another way for us to compose thickets is doing extending them with different columns. And so in this case, we are looking at data across different block sizes. So this is a GPU run. So we have block 128, block 256, 512, and 1024. And we have problems that we've run the data at a problem size of 1 million and a problem size of 4 million. So we created individual thicket for each of our block sizes. And then when we want to columnar join, we're actually going to put that data as different headers on the columns. So we're going to have block 128 and all of its columns, block 256 and all of the data related to that particular run, and so on and so forth for 512 and 1024. And we do have this table printed out, I think, here at the bottom. Yeah. So once we stitch this or compose this together, you can see if I scan to the right, I have block 128. Let's see if I can get this on here. So block 128 has column spot channel, min time per rank, max time per rank, total time. And then as you can see, we also have block 1024, which also has total time, average time per rank. And so in pandas, you can use block 1024 or block 512 as the unique identifier to extract the particular total time column that you're looking for. So this allows us to have columns of the same name, but it's nested under a unique index, which is block 1024 or block 512. And so you can uniquely grab the columns related to the particular index that you're interested in. And then let me scroll back up here to the tree. So you saw this a little bit in Hatchet. So we are printing to the terminal what the tree structure looks like for this particular application. So this is Raja Perf, which is the Raja Performance Suite. It's a little bit different than some of our other applications in that each of the children nodes is the actual kernel. And then the parent itself is just kind of a way for us to organize the different kernels by the type of work that they're doing. All right, so now that we've looked at the performance data table, we can look at the metadata. So our metadata table, again, is storing information about the run. So this is information like your build settings, which compiler, what version of the libraries you're using. And then we're also storing information about the execution context. So number of ranks that were used, what parameters, what problem size, for example, you put on the command line to run it. And so when you print the metadata table, you can see that the profile here is now the index, which is that unique identifier for the particular performance data. And then for each within that row, you get all the information about build settings and execution context. So things that David had shown, right? So you get the Caliper version, you can get the variant, which is defined by the Raja Performance Suite. Spot channel is another metadata that comes out of Caliper. There's CXX flags, how you built the Raja Performance Suite coming out of CMake, how you ran the application, we store the command line, so on and so forth. And so these can be really helpful for wanting, being able to filter your performance profiles on the basis of how you, what problem size you used or how many ranks you might have run the application with. Okay, so we do have an example of how to filter the Thicket object with respect to the metadata. So in this case, we're wanting to filter this. We've defined this lambda here, which is our filter function, and we want to find all profiles with a GPU target block size of 128. So if we find, let's see if it'll show us that column. It does not. I think it's in between here in these ellipses. So basically, after running our filter function, we can see now that we have 3 rows, which must mean that we had 3 profiles that had a block size of 128. Whereas before, if we look in this metadata table, we had an additional. So we removed one profile from this example because it did not have a block size of 128. Okay, another really powerful function that you can use on the metadata is this group by function here. So this can be a nice way to organize your data by grouping them on particular metadata fields. And so we are interested in wanting to create or organize the data by launch date and GPU block size. And so we use those metadata fields in order to group by on our Thicket object. And so once we call group by, Thicket will say, oh, I've created 3 different objects. And it will show you the unique group by or the unique groups that it found. So because we're grouping on the launch date and the block size, the resulting group is we had a unique launch date ending in 508, another unique launch date ending in 517, and a third launch date ending in 527. This is epoch time. And then we can see that the GPU block size that we have is 128. So we have 3 objects that uniquely fit the cross product of those 2. And then if we're just looking at the metadata, we see that there's one element, one profile in each of our thickets that satisfies that tuple. And then you'll have performance data related to each of these metadata objects that's only going to contain performance data for that particular profile. All right, so the last object within Thicket is the aggregated statistics table. This is actually a graph frame, which is the Hatchet object. And so it contains its own graph, or it contains a graph as well as the data frame table. And again, the aggregated statistics is an order reduction over the performance data table of Thicket. So whereas in the performance data, you might have per multiple profiles per node. In the aggregated statistics table, for each of the nodes in the Thicket object, you'll have one row because it's been aggregated. So when you initially create your Thicket object, this is what your stats frame or your aggregated statistics table will look like. So you'll have a row for each of the nodes that will match in the performance data table. And then the only column that you'll have to start is just the name of the node itself. And once you start calling different statistics functions, it will append additional columns to this stats frame element. So let me skip down real quick. So if we wanted to calculate the median across our profiles in the performance table, you can call this median function on your Thicket object and specify which columns you want to, or which column you want to calculate the median on. And what Thicket will do is append underscore median or underscore mean to your metric name and append that into the stats frame. So again, you might use this to calculate, as we did in like the marble example, calculating noise across multiple trials of the same configuration, and then using that information to make a matplotlib plot. Okay, so let me scroll back up. So we've looked at examples about filtering on the metadata. The aggregated statistics table also has the filter capability. And so in this example, we can filter the table just on the basis of the node names. So this is irrespective of the call path. We're just looking for nodes that match a particular name. And so you can make a list here of the node names that you're looking for, and then create, or I guess call this lambda function here, which is our filter function, using this is a filter stats is our Thicket API. And then when we look at the aggregated statistics table, we can see that our structure only has 3 nodes now, as opposed to the 132 that we started with. Okay, sorry, jumping back one more time. So I showed the median, calculating the median on the total time exclusive. There's also mean calculation on the total time, and you can see that we're appending the underscore mean to that column, and then appending that column into our stats frame table. So you can do median, mean, standard deviation, max and min, for example, are some of the foundational aggregated statistics that we support. So here's a percentiles calculation. So that this is going to append a list of the 20th or the 25th, the 50th, and the 75th percentiles. Let's see. And then the aggregated statistics is a graph frame. So it has a graph as well as the aggregated statistics table. And so you can print out the tree on the stats frame object and pass it the column that maybe you calculated, right? So we were calculating exclusive total time, the median calculation. And so we can use the tree function called here to be able to show those values on our tree structure. And so if I scroll down in this tree, the legend down here will match the metric that I passed in. But all these nodes are from our stats frame. Okay, so these next couple are examples on a Thicket object using the query language, the call path query language, and how the other objects or how the other components get updated. So in this example, this is the starting call tree. We're showing on the stats frame the median total exclusive time on our Roger Performance Suite data. And here we're starting to show some examples of different call trees. We are enhancing our query language docs for Thicket in the hopes that people will be able to kind of, if we give some examples of, I want the root node down to the child node in this particular call path, or I want a subtree rooted at a particular node and down to its children. If we can provide some sort of examples and then users can amend those based on the data that they have, or be able to repurpose and extend them to do the queries that they're looking for. So in this example here, we are only selecting the parents and the children of our algorithm-based kernels. And so we are still grabbing the root node in this case. We're looking for this row name that matches algorithm and anything that follows. And so the resulting call path or the resulting call tree after we apply that query is shown here on the bottom. So we started at our base CUDA node, and we're only grabbing the subtree that's related to algorithm and grabbing all of the kernels and the children underneath that are related to algorithm. In another example, or I guess in a similar example, now we're only wanting to grab a subtree. So we've changed that from a star to a dot. And we're wanting the subtree to start with algorithm and grab all of the children underneath. So now you can see we're rooted at algorithm and grabbing all of the algorithm-related kernels underneath that parent node, whereas prior we were grabbing also the root node, which was base CUDA. Okay, so I think the last two examples are visualizations. So within the stats frame, we have some built-in plotting functionality that could be of use. One is the histogram, allowing you to look at a particular metric value from the performance data table and a particular node to print out histograms such as this. And let me see if I know what the metric is. Okay, so we're looking at the total exclusive time here. We're grabbing the first element in our performance data table, so I suppose that might be the algorithm node itself for this particular histogram. But basically, we would have a histogram for each of the nodes of interest and be able to look at the frequency in which particular metrics are occurring. And then the last visualization that we provide, or that we have an example of here in the stats frame, is a heat map. So in Thicket, you can call display heat map and select columns from the performance data table to generate this heat map. And so it can render very small based on how many nodes you have, but on the y-axis here is the node. And then you get a bin or a histogram on the x-axis for each of the metrics that you're interested in. And then the color map here will change based on the number of metrics or based on the range of the metrics that you're looking at. So we're finding that, if you select two different metrics that have vastly different ranges of values, that might not be so great for a visualization because you really cannot tell. You'll find that this all becomes black or all becomes white, and it becomes very hard to distinguish which metric value fits into which color bin. So we do suggest trying to identify metrics that are in similar ranges or creating separate heat maps for metrics that have different ones.